Technology, it is extremely demanding. You have to be smart, intuitive, and you really have to know what you do. You have to learn a lot, but the problem is after you finish the school, you do not have to relax because the technology is changing very fast. So you have to keep up with it, otherwise you will not be a technician. We all know that an air handling unit does not only circulate the air to the system, but it conditions the air, it filters the air, it's cooling the air, heating the air, remove or add moisture into the system. So I want you to come with me onto this little journey so you understand how the air conditioning and air handling unit works. You just see now the primary cooling coil start and is conditioning the fresh air intake. It removes humidity while it's cooling it down. But watching further onto this AHU, you will see that the return air, the recirculated air, is not cooled yet until now when we start the trimmer. Now we have a better control on air cooling. Sometimes, unfortunately, some old design implies glycol that cools the heat exchanger, and that glycol run on negative temperature. This example I'm going to give you, it is about a system which runs with glycol at minus 15 degrees Celsius. So the coil becomes, the heat exchangers become very cold, and the cooler it gets, the more ice sits on the heat exchanger, and the more ice sits on the heat exchanger, the more restriction it will apply to the airflow until it can reach the point where there won't be airflow at all. This is a dangerous situation because in pharmaceutical industry we have to take care of the air change rates and pressure cascade. But technicians are smart. They said, well, I'm going to put a damper and I will close the damper and I will put the heat exchanger on defrost. I will melt the ice and then it will restart its cycle again. This thing doesn't work for pharmaceutical industry because once you restrict the airflow, you lose the air change rates and the pressure cascades, and that will lead to a disaster where you might lose the entire product you just built. So this is the system I'm talking about. You have an air handling unit which provides air to a group of rooms where the production takes place. You don't want to restrict the air here. That's why you have to make sure that the heat exchanger never ice up. But what am I going to do? Because the system, it is already using minus 15 degrees glycol. I have to build a buffer. I have to reorganize the pipes. I have actually to change the design and the control philosophy. But some engineers, quite smart, they thought, well, why will not just build two sets of heat exchangers, like here, and we can alternate them. When the first one comes, the one which is on duty is icing up, we can put it on defrost and bring another one on duty. And as you will see here, they are alternating the heat exchangers, which is a good idea, but there's a little bit of problems here. If you alternate this heat exchanger, if you look at this trend, you'll get this kind of results. The humidity will run up and down a lot, and the temperature won't be very stable unless the premises is huge. So all this because we have to use the minus 15 degrees glycol. Now coming back to my story, you will see here better that this air handling unit is using two heat exchangers. One is on duty and one is on defrost. The one which is on defrost have the dampers closed. You do not want to circulate the air through the very hot heat exchanger which is on defrost. And then on the right hand side you have two gauges. The gauges are measuring the pressure drop across the heat exchanger. So it's kind of monitoring the ice contamination. This is somehow okay, but as I told you before, because you're using minus 15 degrees Celsius glycol, slowly the heat exchanger on duty starts to build ice. And how do we know this? It is very simple. The more ice the heat exchanger builds, the more pressure will be shown on the top pressure gauge. And in this way we know that we have a bigger differential pressure across the heat exchanger, and the ice starting building up. And sooner you will see more ice will build up on the heat exchanger and the pressure will go higher. Now the technician adjusted the defrost time to switch just in time this heat exchanger. But this system, it is not really what we want. Look, in this case we lost the entire airflow. There's no airflow. And if you don't have the airflow, you can jeopardize the production of such important medical things we do. And why all this happened? If you look to this little footage now, you'll see. The technician used a timer to decide how much the defrost will be applied. But that timer doesn't understand the nature. It could be cold, warm, rain, steam. And because of this, we decide to fit into this heat exchanger a defrost termination probe, which actually is not based on a time, but is evaluating the ice quantity on a heat exchanger. And that helps us to optimize this system so we get the best out of it. However, I personally disagree with this system. I would rather do something else. I will build a buffer and I will use 2 heat exchangers in the same time, running the glycol at a higher temperature. In that case, I will increase the area by adding 2 more heat exchangers, and I will increase the glycol temperature probably at -1 or 0, and in that case the air will pass a bigger area. I will drop enough quantity of energy. I have a smoother trend and I will not have an ice up phenomena anymore. The heat exchanger will never build ice and I don't have to use the steam, and that will save a lot of energy. So yes, we are a technician, we're smart, we understand control, we understand a lot of things, and I think we'll always find solution for a better air handling unit. Thank you very much.